is Professor Lino Reséndis. Lino Reséndis is going to talk about Bicomplex Bergman projection. Okay, Professor.
Okay, let me know if I can share my screen, okay?
Okay, yes.
No. Wait a moment. Okay, I am sharing my screen. It's okay?
We can see now, yes. Okay.
Okay, so Control L. Okay, so first I would like to thank the organizers for this invitation to talk in this fest. Really, I am very happy to be here, and Professor Enrique. I would like to thank really all your experience, your expertise in the math department at Simba staff. Also, I am very proud to have the opportunity to talk in this conference. Okay, the title of my talk is Bicomplex Bergman and Bloch Spaces. Okay, this is the plan is first I will give some preliminaries. After we will introduce bicomplex weighted measure, then the bicomplex Bergman space, and if we have time, we will mention some facts about the bicomplex Bloch space and relation with the bicomplex Bergman space. More in particular with the Bergman projection. Okay, first let me to say some words about this theory of bicomplex numbers. The set of bicomplex numbers that we denote by BC is defined in this form: C1 minus G C2. Here we are introducing a new imaginary unit, G squared equal -1, in such a way that E times G, the product of both imaginary units, are equal to K, and they commute. And sum and product of bicomplex number are present in the expected way, like in the complex, okay? The structure of these bicomplex numbers suggests three conjugations. The first one, Z bar, given in this form, C1 bar plus G C2 bar. C dagger conjugation, C1 minus J C2, and Z star conjugation, given by bar C1 minus G bar C2. In particular, if we multiply Z by Z dagger, it's by this conjugate, we get C1 to square plus C2 to square. And this is an algebra with that has zero divisors. In particular, the bicomplex number C1 minus GC2 is a zero divisor if and only if C1 squared plus C2 squared is equal to 0. Equivalently, we have this inequality. Then it's necessary to recall that we have then zero divisors, and we characterize exactly zero divisors by this equality. Okay. It's possible to represent bicomplex number in many different ways. Okay. In this moment, we will introduce the idempotent form of some bicomplex number. Okay, in the following form. Okay, we can represent the same bicomplex number Z in this form: Z equal to beta 1 E plus beta 2 E dagger, where beta 1 is given in this form, C1 minus IC2, beta 2, C1 plus IC2, where E is given by 1 plus times EJ over 2, and E dagger in this form. The difference is only with the sign. In particular, we can observe that E dagger is equal 0. The product of this bicomplex number is equal 0. And we can represent any complex number, usual complex number, by lambda times E plus E dagger. Okay? And then this is very important representation for bicomplex numbers, and it's called idempotent form. With this notation, all zero divisors in bicomplex number can be written in this form: Z equal lambda E or Z equal lambda E dagger, with lambda a complex number. Then we have this line, this complex line of zero divisors in bicomplex numbers. Now, we will consider here only the conjugation Z star. Z star, this conjugation can be written in idempotent form, like only if we conjugate beta 1 and if we conjugate each component in the idempotent form. With this conjugation, we have, in particular, we have that the product Z star is given in this form: modulus of the complex number B1 to power square E plus modulus of beta 2 to power square E dagger. And the inverse of Z can be written in this form. Okay, of course, Z is not a zero divisor. And we define the k-norm of Z in this form, the square root of Z star, and it's given exactly by this: modulus of beta 1 E plus modulus of beta 2 E dagger. Or more in general, for instance, if alpha is a real number, we can write this power in this form. All this belongs to the theory, okay, B1, B2, beta 1, beta 2 greater than 0. All these facts belongs to the general theory of bicomplex numbers. And in the special case, when we consider two bicomplex numbers, where coefficients, real coefficients in each component in this idempotent representation, then we can give this partial order lexicographically. Okay. In particular, then if we have this with this order, with this partial order, it is we will say here key norm. Of course, it's not exactly a norm, but I will say key norm. If this norm, and I will read this like less than 1, less than 1, but of course recall that this is partial order. Then, in particular, if we calculate this bicomplex number, then the power alpha can be written in this form: 1 minus modulus of beta 1 to power square to power alpha, 1 plus E plus 1 minus modulus, square modulus of beta 2 to power alpha E dagger. Okay, well, now we consider omega a function, we consider a domain in the bicomplex space, in the bicomplex set, and we consider a function defined in a domain in omega. The derivative of omega is defined using the differential quotient in the usual form, as you can see. Of course, C minus C0 is an invertible bicomplex number. It's necessary to avoid, of course, zero divisors, okay? And we will say that F is Bicomplex derivable in omega if we can calculate this limit in each point of omega. Okay. Of course, Bicomplex numbers, okay, is a subset of is R4 with some special operations, okay? And in particular, with this definition, we can see that if F is a bicomplex holomorphic function, then satisfies the Cauchy-Riemann system. As you can see, this Cauchy-Riemann system is the equivalent to the classical Cauchy-Riemann equations. But instead of X or Y variables, we are considering C1 and C2 complex variables. But this is analogous. We have the following characterization also. If we consider a bicomplex function f defined in omega of class 1 C1 with this idempotent decomposition, okay, then we have each component depends of beta 1 and beta 2. G2 is the first component, G1 is the first component, G2 is the second component, and both components depend of beta 1 and beta 2. Okay, then this function is bicomplex holomorphic if and only if we can forget the second variable here. For instance, here, BC is bicomplex holomorphic if G1 depends only of beta 1 and depends holomorphically, and G2 depends only of beta 2 and is a holomorphic function. G2 is a holomorphic function of beta 2. This is really then a powerful result about these bicomplex holomorphic functions. Its derivatives of any order are given only taking successive derivatives of each component. Here you can see only variable beta 1, and here only variable beta 2. And the rules of derivability are the usual rules. Okay, we will denote the unit disk in the classical complex set by U. And the bdix U in the bicomplex, it will be the product type domain. Okay, we will write in idempotent notation in this form. Okay, then each coordinate beta 1, beta 2 belongs to the classical unit disk. And then we can consider this bdix with this like this Cartesian product. Okay, now we have here, we consider a domain in the bicomplex numbers, okay, or R4, okay, and we consider a function. And then now we write this function using the idempotent notation. But now we will consider the respective real variables, okay? Here you can see this is beta 1, this is C1 minus IC2. Recall that this is the change of variables. And then we consider only the real part and the imaginary part. And then this is the real part of beta 1, and this is the imaginary part of beta 1. And now beta 2. This is C1 plus I C2. And the imaginary part, the real part of beta 2 is this, and this is the imaginary part of beta 2. The Jacobian matrix of this change of variables then is given by this matrix. Okay, we have four functions and four functions and four real variables. Then this is the Jacobian matrix and has determinant 4. Now, then in particular, if we have a bicomplex integrable function, then we integrate this bicomplex integrable function on the disk. Okay, this is the normal volume measure. Then we integrate, this is if we use the classical notation of the bicomplex variable. But now we can change to the idempotent notation. Then it's necessary to consider these 4, that this is the Jacobian. And of course, and now, okay, now we will consider, okay, this is the normal volume in the disk, okay, in the disk. Now we consider the normalized Lebesgue area, okay, in C, okay, given by this because it's normalized. This is the normalized area. Then let me to introduce now the bicomplex weight measure dB alpha for each in this bicomplex case. We consider alpha greater than -1, okay? And we introduce this weighted measure, okay? This is in some sense the standard weight measure, okay? And we introduce alpha plus 1/4, 1 minus square of the key norm to power alpha, dx1, dg1, dx2, dg2. This is the classical Lebesgue measure, okay? Volume Lebesgue measure. But now we can rewrite this expression using idempotent representation. And then we have this. But now we are changing coordinates. Now we are using coordinates beta 1, beta 2. And then this is our new volume form, okay? And if we apply them, we can see, because this factor, then here we get the usual weight measure in the unit disk given by this. And here is only the normalized measure in beta 2. And here there is the another situation. This is the usual normalized measure of the unit disk, and this is the weighted measure, the alpha weight measure in the disk. And then we have this. This will be the bicomplex weight measure, dB alpha. Now, passing to polar coordinates, and by definition of the gamma function, we get this result. If we consider m and n be two non-negative integers, then if c is equal to this bicomplex number, okay, we can calculate then the integral on the disk of the product of these two monomials, zeta m and zeta star n, according to the weighted measure dB alpha. Okay, if we write this integral in its idempotent form, then we get this result. Is equal 0 if m is different from n is equal to this number, of course, in terms of the gamma function, if m is equal n. Okay, this calculus is very important Okay, all the people that, of course, here knows that this type of result is very important in the theory or on the classical theory of Bergman space. And in particular, maybe you can guess now that I am only trying to translate the results of the classical Bergman theory to the case of to this Bicomplex case. Okay, and this is the key to get these results. Again, we can show that if we have two Bicomplex numbers C and W in the unit disk, then we can also obtain this power series development for this quantity, 1 over 1 minus C W star to power lambda. And we can write in this form. You can see here, this is the constant, and here appears the variables, the respective variables theta n, W star n. Very classical result. Bien. From this proposition, we get the following lemma. It's possible to estimate this integral. See, alpha is greater than -1. Eta is any real number. And we have this estimation that depends. Here the power is 2 plus alpha plus eta. And this estimation depends of eta. If eta is less than 0, eta equals 0, or greater than 0. Here, of course, it's necessary to see each component, okay? It's necessary to see each component. This is comparable, but it's necessary to see each idempotent component. And here, of course, this logarithm is the Bicomplex logarithm function, okay? It's the Bicomplex logarithm function. Now, we introduce now the Bicomplex Bergman space, okay? We denote here the Bicomplex Bergman space, weighted here alpha, Bicomplex Bergman space in the B-disk, and consists of the space of Bicomplex holomorphic functions, Bicomplex holomorphic functions in the complex space LP with this measure defined in the B-disk, such that then we have this integral and is less than infinity. But recall this is the K-norm. It is necessary to look for each component. Okay, each component then is bounded. Then this is the weighted Bicomplex Bergman space. Now, this theorem say us that in particular, if we consider p greater than 0, alpha greater than -1, then we can decompose the Bicomplex Bergman space as the sum, in some sense, the classical Bergman space in the first component, E, plus the classical Bergman space in the second component, E dagger. Okay? And in particular, if we write F, this bicomplex holomorphic function with components G1 and G2, then if we estimate the definition, the integral definition of Bergman space is exactly, see, in this form. Exactly the definition of the Bergman space in the classical unit disk E plus the classical Bergman space here in the disk U, E dagger. Okay, the proof is very easy because we know exactly the measure that we are using. Okay, then we make this multiplication. It's necessary to recall that E por E is equal E and E por E dagger is equal 0. By this reason, then when we make this multiplication, then we get this integral. Here appears the weighted measure with respect to the beta 1. And here is the normalized Lebesgue measure of the unit disk, and the same result in the second summa. Then we separate, see, we iterate the integral. Okay, this is with respect to beta 1, this is with respect to beta 2, but this integral is 1 because the measure, the Lebesgue measure, is normalized measure. Okay, we separate, this is equal 1, and then we get this. And in quite similar form, we get the second summand. Okay, and then, bueno, now we consider the key norm of F. Okay, of course, I am saying key norm, but exactly is not a norm. Okay, we consider power 1 over p, but we can put the power 1 over p on each component, and then we get our result. Now, we can also to prove the following. If p is greater than 0 and alpha is greater than -1, every point evaluation in the unit disk is a bounded linear functional on the Bicomplex Bergman weighted Bergman space. And also the weighted Bergman space is a closed space in the respective LP space, of course with the volume with the weighted volume measure. And also for every function in the Bergman space, we can find a sequence of polynomials, a sequence of bicomplex. Okay, here, sequence of bicomplex polynomials that approximate in this key norm our function f. Now we consider the case p equal to. Since the bicomplex Bergman space is complete, and we will see that it's a Hilbert space, we define this monomial S sub n of c equal to this constant monomial z, the bicomplex variable, to power n. Then, of course, now the set of these special monomials is an orthonormal set in L2 bicomplex space. Okay, here is the measure. Here should be the measure. In particular, it will be a basis for the space, for the Bergman space. Okay, the proof, it is almost directly, because then, of course, the inner product is defined by this integral on the B disk. We consider the monomial S sub m times S sub n star. Recall conjugation, this special conjugation, okay? And this is the weighted measure, okay? And then this is a constant, this is a constant. We can write outside of the integral, and then we calculate the inner product of these two monomials. But in fact, this was calculated in some result at the beginning, and then this is the Dirac delta Mn. Okay, and since the complex polynomials is a dense set in the Bergman space A2, then this is an orthonormal basis of whole this space. Now, in particular, if we choose another function g in the Bergman space A2, weighted Bergman space A2, with this representation of each function in power series using the variable z, then, okay, each n can be written in his idempotent coefficients. And Bn, of course, this is the idempotent expression. Then Fc and Gc can be written in this form. Please observe here only beta 1 to power n, beta 2 to power n, and so on. And then if we calculate the inner product of F on G, then we get this expression. We get this expression, okay? Here is conjugate, here is a conjugate, okay? This is the normal conjugation, of course. And in the special case that F equal G, then we get this classical series development, okay? As you can see, we are recovering the classical results in the classical Bergman space. And then this, the coefficients are quadratic summable, okay? Then, okay, I am repeating this result because now we want to study the following result. We consider alpha greater than -1, and we will consider the orthogonal projection we call pk alpha from the respective A2 weighted space to the A2 Bergman, Bicomplex Bergman weighted space. Then the Bergman projection of F, if we consider some function in L2, is given by this formula. Okay? Then this will be, in one moment in this talk, it is necessary that some kernel should be appear. And now appears this kernel, okay? Well, the proof is quite standard because now we have some orthonormal basis of A2, of the Bergman space A2, the complex Bergman space A2. Then we expand the projection. The projection belongs to the Bergman space. Then we can expand the projection in power series. Here's this projection. But now, if we study each coefficient, see, because it's self-adjoint the projection, then we can interchange here in the inner product, and because the monomial S of n belongs to the Bergman space, then is the identity allí, the projection. And then we have this, then we calculate using our definition of inner product, and then we get this. And now we go to our power series expansion, our series expansion in terms of the basis of the orthonormal basis. Now we can change this inner product. We substitute the value of our monomial, and now we interchange because the summation is quite justified. We can interchange the integral and the summation, okay? And then we get this, and all this expression, all this series that appears here is precisely the function y minus c w star to power 2 plus alpha. And then we are done. Then in this form, then we have that this set of functions are exactly the weight Bergman kernels of the B-disk. We have this. And the idempotent formula of these kernels are exactly this, where these kernels are the usual weight Bergman kernels. But with respective variables, beta 1, gamma 1 here, and here beta 2, and gamma 2 here. Okay, now we consider the following result, because maybe we can expect, okay, we have the Bergman projection, and then maybe the Bergman projection factorized in two Bergman projections, okay? Now we have this, okay? We consider the weighted Bergman projection from L2 to the Bicomplex Bergman space. Okay, then the action of the Bergman projection is the usual Bergman projection in the Unite disc, but not on G1 like here. G1 hot. And also here, the usual Bergman projection, but in G2 tire, G2 hot, not G2 exactly. Observe that this is the idempotent notation for F. However, we need to apply the usual weighted Bergman projection to these functions. Why? But it's very easy. Okay, you can see here the Bergman projection of F. Then this is idempotent notation. The integral is on the disk. Okay, but we have both d sub alpha gamma 1, and this is the usual normalized Lebesgue measure of the Unite disk. Okay, but now here, if we see, for instance, the first component, then we decompose this integral over the BDs over the U1 and U2. And we integrate G1 with the normalized Lebesgue measure of the Unite disk. It's here in this numerator. And here is the weighted measure, usual weighted measure of the Unite disk with this kernel. Okay, usual kernel of the Bergman. And then by this reason, the factorization of the Bergman projection is like this. Here is not G1, is not G2. It's necessary to consider these integrals instead of G1 and G2. A little bit different from the expected result. Okay, then of course, and then if F is a function in the Bergman space, then we apply the Bergman projection and we recover F. Then we have this. These are reproducing formula for F. Then these are reproducing kernel. And then, in general, if F is a function in the Bergman weighted space, then we have this representation. We can represent each B holomorphic function in the Bergman space in this form. Okay, well, now we will try to recover another results connected with this beautiful theory. In my opinion, it's a very beautiful theory. Okay, and what? Okay, and here in this conference, in this congress, there is a lot of persons that are better experts than me. Okay, I am maybe I am giving a very elemental lecture, but okay, I will continue. Let's begin the Bergman projection, and we consider Fn two non-negative integers, such that m plus n is greater than -2, and rho plus alpha is greater than -1. And then we calculate the Bergman projection of this function. Of course, these functions belongs to the L space, okay? It's bounded, okay? L1 space, okay? Of course, it's not, of course, you can see, is not bicomplex holomorphic. It's not bicomplex holomorphic. But of course, if we apply the Bergman projection, should give us a bicomplex holomorphic function. And exactly is this? Is 0 if m is greater than n. But if m is greater or equal than n, then is all this constant, horrible constant here, no, and this monomial. Okay, this monomial. Okay, the proof is quite standard. Okay, Why? Because we apply only our formula of the Bergman projection here. It's here. You can see here. Here is our kernel, weighted kernel. Okay. We develop in power series the kernel. It appears here. Okay. And now we interchange the sum and the integral, and we get this. And again, we use the fact that we can calculate this, okay? Because here is the weight measure. You can see here, this is the normal Lebesgue measure, and here is the weight. And then we get in a direct form. Then we have this result, and now another result in this line. See? Now we can consider rho a non-negative integer. We consider this bicomplex holomorphic function because it's written in a power series, okay? But L starts and 2 rho plus 1 to infinity. Then we consider the Bergman projection, but of this function, okay? Of this function. There is no problem. Okay, Z should be not zero divisor, of course. And here is the rho derivative of F, okay? And then the Bergman projection of this function is this constant plus this power series, okay? And this is, of course, a bicomplex holomorphic function. Or if we pass this constant to the other side, then we have this, exactly this. Then it's possible to make all this calculus, but as a corollary, see, from this corollary, we can see that the Bergman projection is onto. Okay, now we consider F an arbitrary bicomplex holomorphic function in the Bergman space. Okay, in the Bergman space, bicomplex holomorphic function in the Bergman space. Okay, and we define this function EC. As you can see here, all this part, of course, is not bicomplex holomorphic by this factor. Okay, again, this part is not bicomplex holomorphic because we have this factor. This factor is not bicomplex holomorphic times this series. Of course, this is bicomplex holomorphic, but in general, this function is not bicomplex holomorphic. Okay, but there is no problem, belongs to the space LP. Then the projection of E of this function E is exactly F. By this reason, well, using our previous result, we can see that the projection of this function is exactly F. By this reason, the projection is onto. Now, we can prove also these two results, very similar to the classical results. If alpha and eta are greater than -1 and p is greater or equal than 1, then our Bergman projection is a bounded projection from the respective LP space on our respective AP Bergman space if and only if alpha plus 1 is less than eta plus 1 times p. And also we have this proposition. If p is greater than 1 and alpha greater or equal than 1p and alpha greater than -1 and n is a positive integer, then a bicomplex holomorphic function f in deep disk belongs to our Bergman space, weighted Bergman space, if and only if this function clearly is not holomorphic, if and only if this function is in LP. Weighted, or in our weighted LP space. Okay, now, because I have maybe 4 minutes left, I will introduce, let me introduce the last part of our talk, que es bicomplex block space. We can define for a bicomplex holomorphic function f, defining the bicomplex block space. And then in the usual form, then it will be the supremo of 1 minus c k naught to power square times the derivative of f in the k naught. If this supremum is finite, recall, it's necessary to look each component, then we say that f belongs to the block space. Okay, we can also to prove some bicomplex version of the Schwarz-Pick lemma. And we can see that this block, bicomplex block space is Möbius invariant. Okay, but of course, again, it's necessary to say this is a bicomplex Möbius invariant. Okay, in that sense, bicomplex Möbius invariant. Okay. The little block space, if this vanishes on the boundary. And we can also define some norm in this space, given in this form. We add the value of f of 0. Okay, with this will be we say key norm, but of course it's necessary to see each component. And with this key norm, the block space, the bicomplex block space is complete. Okay, well, here also it's possible to see the idempotent decomposition of each block space corresponds to the block space in each factor, or in each summand, quizás is better to say, in each summand, okay? And by the bicomplex Schwarz-Pick lemma, we get also this estimation. And we can see then that all bicomplex bounded function belongs to the block space. And okay, I have only 1 minute, and then only I will present the last result. Okay, if alpha is greater than -1 and pk alpha is the corresponding weighted Bergman projection, we can map with the Bergman projection, with the Bergman projection, all the space L infinite of the BDs in a bundle form onto the block space. And if we consider continuous functions on the until in the closed BDs, unit BDs, then we can map all this space also bundling on the little block space. Okay, well, let me to finish this talk. Congratulations, Dr. Enrique Ramirez de Arellano. Muchas felicidades. I'm very happy to be here and to participate of this Congress. Thank you very much for the organizers to give me this opportunity to talk here. Okay, I'm done.
Okay, we thank Professor Reséndis. Any question or comments? No? Okay, our next talk will be at 11 with Professor Tovar. So we can rest 5 minutes, 10 minutes.